Okay, in this video, I'm going to demonstrate how you can carry out tests of interaction effects when you are running HLM, and this is using the STATA program. Um, the data is basically student data with students being nested within schools. Our level one outcome variable, if we want to take a quick look at the variables, our level one outcome variable is math achievement. Our level one predictor at the student level is the variable female, which is gender coded 0 for male, 1 for female, and SES, which is socioeconomic status associated with the schools. The ID variable is the student identifier within the data set. The level 2 identifier variable is the school code variable. So we have the students who are nested within schools. So, essentially we have, all of these students right here are nested within, school 1. Then we have those that are nested within school 2 and so forth. The level 2 predictor variables in the model are sort of a school average of the students' SES, so kind of getting an idea of overall the average student SES within the schools. Proportion of students within the schools that are intending to attend a four-year college, and then an indicator variable for whether the school is a public, which is coded 1, or a non-public school, which is coded 0. So, what we're going to do is I thought I would pretty much walk you through some different models and using or walking you through the basic models using syntax. So I have it actually in a do file, but I'm going to walk you through this instead of kind of running this as a batch. So basically, in terms of the syntax for carrying out the HLM model, we're going to use the mixed command, and then we have, following the mixed command, we're going to follow it up with the level 1 outcome variable. So this is pretty much the same format that we use when we're running a regression through STATA. We have the command followed by the dependent variable, and then we follow that up with the names of the independent variables that are being included in the model. So you'll notice that, and so these are all reflecting fixed effects within the model. So SES is a level 1 predictor variable. So we want to calculate the regression slope for SES at level 1. Then we have the female variable, which is also a level 1 predictor. So again, it's coded 0 for male, 1 for female. So these two are level 1 predictors. Then we have, these variables right here are level 2 predictors. So proportion of students intending to attend a four-year college, the average SES associated with the schools, and then also, whether the schools are public or non-public. Over here, you'll notice that we have interaction effects that have been laid out. This is for a cross-level interaction, which is basically looking at the interaction between the level 2 predictor of public and the level 1 predictor SES. Then this is also this is basically an interaction between the level 1 predictors. So this is basically sort of a within level interaction. And before I kind of break this down a little bit further, I'm going to go over here. You'll see we've got two vertical lines as part of the syntax, and then you've got the name of the level 2 identifier variable, which is the school code variable right here. So it's followed up with a colon. Now you'll see right here we have SES that's being included, and SES, we have the fixed effect of SES right here, and so what we're computing right here is essentially sort of an average slope across schools for the effect of SES on math achievement. But we also want SES to randomly vary between schools, and the reason why is because we might presume that the slopes are varying across schools, and then we can model a cross-level interaction between a level 2 predictor and the variation in slopes at level 1. So in other words, we're really kind of trying to predict variation in slopes for SES at level 1 as a function of the public variable right here. The idea being that maybe the slopes differ depending on whether the school is a public or non-public school. So that's capturing a cross-level interaction between the public variable and the level 1 predictor SES. So in other words, if we're going to model a cross-level interaction, we have to allow the level 1 predictor to vary across the level 2 units. If we do not have this incorporated into our model, if this was excluded from the model, then this would not make any sense, and we couldn't incorporate that interaction. So that's the reason why that's in there. If it were the case that we were going to allow, let's say we wanted to look at public and trying to predict variation in the slopes for the female variable in terms of predicting math achievement, then we would also be incorporating the female variable as a random slope variable as well, or a variable that associated with the random slope as well. So that's how it works. So we're not going to do that. We're just going to leave SES as we're going to allow the slopes to randomly vary across the schools, thereby allowing us to model the cross-level interaction. This interaction term right here, you can see we've got female by SES, and so this is the within level 1 interaction effect. You'll notice that, and so obviously we don't need to incorporate any kind of random coefficients over here. You'll notice that in both of these cases, SES has a little C prefix or a C period prefix to it. And so that's denoting the fact that we're treating SES as a continuous variable. When you are and you'll notice that the interaction term is reflected in by the pound sign as well. So we have a pound separating our variables that are making up the interaction. So we only really need to use the C prefix when we are modeling interactions between variables, and we want to denote a variable as being continuous. So SES is being treated as continuous. If we don't incorporate the C prefix, then it's basically going to treat the variable as this variable right here as a factor. And so there you go. We could have also, if we wanted to treat it as a factor in the model, we could have used an I period prefix right before it, and that would have sufficed. Notice that we don't really need to say anything about the other variables over here in terms of whether they're factors or continuous variables. We only need to make these specifications mainly when we're dealing with our interaction terms. So let's run this particular analysis right here. So I'm going to hit enter. And so as you can see, we've got our effects over here, regression coefficients and significance levels. So SES has a positive regression coefficient indicating that students with a higher SES tended to perform better in terms of math achievement than students with lower SES. That predictor was significant. In terms of the female variable right here, you can see it's a negative coefficient. We coded males 0, females 1. So the negative coefficient indicates that males were performing better on math achievement than females. That coefficient was statistically significant. When we look at the level 2 predictors, proportion associated with the schools intending to attend a 4-year college, that coefficient was significant. So basically within schools with greater proportion of students intending to go to college, they also exhibited greater levels of math achievement. That was significant. The coefficient for the SES mean variable was positive and significant, indicating that schools comprised of higher SES students tended to perform better in terms of math achievement than schools with lower average student SES. Then for the public variable, you can see it's non-significant. The negative coefficient would just signal that schools that were not public schools would have scored a little bit higher in terms of math achievement than the public schools. And that's because the 0 was associated with the non-public schools, the 1 being associated with the public schools. Then we have the interaction term right here. You've got public by SES, and so there's the regression coefficient and the significance test. So we see that that interaction term was statistically significant. The interaction between the female and SES at level 1, there's the coefficient, and you can see that that was not significant. Typically, you would probe a significant interaction and sort of pay less attention to non-significant interactions. So, but we're going to probe really both of these just to kind of demonstrate how you can do that using the STATA program. Just so you know, another option from using syntax, we could have just as easily used this syntax right here in terms of generating our model. You'll notice that what I've done is I've incorporated, there's the mixed command, math, then I've got SES, proportion attending four-year college, SES mean right here, then public, and then you've got the double pounds, and then SES, and then female, and then double pound, and then SES right here as well. We still have SES also incorporated over here to allow that slope for SES to randomly vary across the schools. But the deal is that when you'll notice that we don't have public appearing before or female appearing before. By using the 2 pounds, it's basically going to generate, that's for a full factorial, and essentially it's going to generate the individual effects as well as the interaction terms. And in fact, you know, so yeah. So at any rate, what we're going to do at this point is I'll hit enter and I'll just kind of show you what it looks like. You'll see we have SES right here, the intention to attend four-year college, the school level SES, and then the identifier for public or non-public right here. So these coefficients are all exactly the same as what we had above. You know, and there's the p-value for that as well. You'll see that SES appears and it says omitted, and that's because, you know, using that double pound, what it's going to do is it's basically going to generate any variable that's falling on either side of the pound sign. So that's why the SES, it was going to generate that, but instead, because we had included SES above, it says, well, we're just going to omit that. We're not going to bother with that because we already have it. The same goes down here for SES associated with the interaction with female. So you can see right here the female coefficient for the female variable and significance level, and then SES is also omitted right here. There's the interaction term for SES and female, and you can see that was non-significant. So, you know, you can do it both ways or either way. It's no big deal however you do it. I probably would tend towards the first option, which is just spelling out the individual predictors and then using the single pound to separate them. And then that just kind of gives me a little bit more control over how it's kind of presented. Also, you know, like I said, the way that we laid this out previously, the model was treating essentially the public variable as a factor. You know, if let's say I happen to have a predictor variable, let's say public was not being treated as a factor. Let's say the public variable was continuous. Then, you know, what I could do is instead of using, I could just use the C prefix there, C period prefix there. And let's say the female variable was also being treated as continuous. Then I can use the C prefix for both of those, and then it'll recognize, the program will recognize those as being continuous. So you can see the presentation's a wee bit different, you know, in that we don't really have the ones right next to the public or the female variables like we saw above. That's because these variables are being treated as continuous. You know, just as a side note, because these variables are dummy coded, then it really didn't matter either way if we treated these as a factor or as continuous. The coefficients are all going to be exactly the same. Where things would differ is if, let's say, we had a variable with, you know, like 3 or more levels, and the variable was not dummy coded or whatever. Then if we treat it as a factor, then it would generate, you know, interactions associated with each of the levels. So So we haven't really done that. So that's basically the reason why, really all of this output is exactly the same as what we've run above the previous two approaches. Now, let's say we want to probe the interactions. So let's start by probing the cross-level interaction. So one way to do that is to carry out simple slopes tests. And so what I'm going to do is I'm going to use the margins command, so it's margins, comma, then a dy dx, and that's just basically saying generate the slopes for SES. So SES is, let's say that's my focal predictor, and I want to see how those slopes vary across levels of the school variable, whether it's non-public or public. So I've got then at, and then inside this parenthesis public equals, and then inside yet another parenthesis 0 comma 1 designating the levels of the public variable. Then you'll notice an end parenthesis, which essentially is kind of wrapping up this portion of the statement right here. So when I hit enter, you'll notice that I've got the dy dx. These are the simple slopes, and so the level 0 is the non-public school, and then the the 1 is representing a public school. So you can see that the slope for the relationship between SES and math achievement is actually stronger in the non-public school as opposed to the public school. And you see that both of those slopes are statistically significant. Now, if I want to get a visual on the interaction effect, I can do that as well. And so what I'll do is I will I want to generate a plot of the predicted values associated with math achievement at different combinations of the public variable and SES variables. And so a common approach when you're dealing with continuous predictor would be to essentially look at generating the predicted scores at a low value, a medium value, and a high value on that continuous variable. And so one kind of arbitrary way of doing this, but it's still a way, is to treat one standard deviation unit below the mean as a low value on SES, the mean as sort of the middle value, and then one standard deviation above the mean as being a high value. So and so really what you can do, the easiest way to do this, if you don't want to compute everything using a different calculator or whatever, is what we can do is we basically say tab stat SES comma and then statistics, and then type in mean and SD in parenthesis, and then that will get us the mean and standard deviation for the variable. And all I want to do is I want I want to plot at one standard deviation below the mean, so that's just basically the mean minus the SD, one standard deviation above the mean, which is the mean plus at the SD, and then at the mean. I'm just going to use the program really as a calculator really quickly to get those values at one standard deviation below and above the mean. So I'm just going to use the display command. So it's just display, and I just typed in this value right here and then minus this value right here, and this is going to get me the value at one standard deviation below the mean is a value of negative 0.749, or yeah, and then above basically it's just going to be putting a plus sign right here, which is 0.81268. So kind of moving down, you can see that now what I'm going to do is I'm going to use the margins command again, and it says margins comma, and then we're plotting predicted values at different combinations of the SES and public variables. So we're going to be plotting at non-public schools at low, medium, and high levels of SES, and then within public schools at low, medium, and high levels. So these values right here, this negative 0.74888 is from this computation right here. The 0.0139 is coming from the mean on this variable, and then the 0.81268 is coming from this portion right here. So at any rate, then we only have two levels of the public variable, which is the 0 and the 1 right here. And so at this point, you'll notice that, like I said, it says at, and then inside the parenthesis, SES equals, and then inside this parenthesis are the levels that we want to plot at. Then we round out the parenthesis and then add in the moderator variable. Level 2 moderator is public, equals, and then inside the parenthesis 0, 1, and then an end parenthesis. And this end parenthesis essentially closes out this entire statement. Then I have plot, and then the no CI is reflecting the fact that I don't want confidence intervals generated. So now when I hit enter, you'll see that I get the predicted values on Y at each of these combinations. So you can see we've got public schools, or excuse me, 0 on that variable is non-public school at low SES. So I'll just kind of use my little marker here. So this is low SES, non-public schools, low SES, public schools. Middle SES, non-public, middle SES, public, and so forth. So, so essentially the means that are plotted down in the table below, those are essentially, those are the predicted values on Y. And so you can see we've got two lines right here. The non-public schools are in blue and the public schools are in red. So you can see that, this one right here, this is a plot of the predicted value for low SES and within the non-public school, which is in the blue. So it's this point right here. Then we've got, again, the low SES, but within the public schools. So you can see that the slope for the public school is less pronounced than the slope for the non-public schools. So that gives us a visual representation of the interaction effect. Now, let's say we want to look at the within level interaction, or the interaction between the two predictors at level 1. So in this case, I'm going to use the margins command again to generate simple slopes and the test of those slopes. And I'm using female variable coded 0 for male, 1 for female. So when I press enter here, you'll notice that I get the simple slopes. So for males, the relationship is 2.97. That's the regression coefficient. It was significant. For females, again, a positive coefficient, significant. But you do see that the relationship between SES and math achievement seems to be a little bit more pronounced among the females. If I want to, generate the plot of those simple slopes, you can see that I'm just basically using the margins command again, comma, and then at, then SES. So all of this right here is exactly the same as what we had above when we plotted out the simple slopes. You'll see that now we've got female is and equal to 0, 1 for males and females. So the command structure is exactly the same as what we had previously. And when I hit enter, you'll see that I get the plot. Remember that the interaction effect, or the interaction term at level 1, was not significant. So we would expect the slopes to be reasonably equivalent. You'll notice that this is a little weird, and the reason why is because, and I made this mistake earlier when I was copying and pasting the syntax, I failed to include a negative in front of this 0.74888. So there you go. So that's what happens when you get your forget to include a little negative sign where it should be. So at any rate, we'll replot this. There you go. So as you can see, this is low SES, and then for females, this is low SES females, low SES males, middle SES females, middle SES males, and then high. And so you can see the slopes are pretty much parallel, and so that's reflecting that notion that there's really not an interaction effect that was taking place. So there you go. One other thing to kind of note is that, right here, when we were plotting this out, let's say, for instance, that female, let's say that this happened to be, let's say this wasn't female, but it was some other variable that was continuous. Then what we could do is we could end up, generating low, medium, and high levels for that variable, just like we did with SES. And then instead of having, the 6 plot predicted values, we would actually have 9. And so, we would just basically incorporate, the additional values, whatever it would be. There's a 7 or 9 or whatever. And so it functions in exactly the same way. So at any rate, that pretty well concludes this presentation, and I hope you find this useful.